Hello and welcome to another video. In this video, I'll show you how to access and explore global bathymetry and topography data in Python at a resolution of 15 arcseconds. We'll start by pulling the data straight from a netcdf file hosted online, and then we'll create a 2D map for any region that you're interested in. And if you stick around to the end, I'll show you how you can build a fully interactive 3D visualization like this one, where you can zoom in, rotate, and instantly read off the relief at any point where your cursor is pointed at. This tutorial is accompanied by a written tutorial that you can find online, and there's a link to this in the description of the video. It includes all the code that we'll go through today, and some bonus code as well for if you want to learn how to do a few extra things that I won't go through in the video today. The dataset we're going to look at today is the ETOPO Global Relief Model provided by the National Centres for Environmental Information, part of NOAA. I've provided a link to the landing page for this dataset in the description of the video, so go and read more about it there. And if we scroll down, we can see that the data are provided in a few different formats in GeoTIFF and netcdf, and in different resolutions as well. We're going to work with the data in netcdf format, and we're going to take the highest resolution possible, the 15 arcsecond resolution. You can see that there's three main datasets here: the bedrock elevation, the geoid height, and the ice surface. And so the bedrock is the base of any ice sheets that are there. And these data, if we go and look at them, mainly cover Greenland and Antarctica. I have another video where we make a map of what lies below the ice sheets in Greenland and Antarctica. So if that's what you're interested in, go and watch that video instead. So what we're going to take is the ice surface elevation netcdf, and the data are divided into 15 by 15 degree tiles that cover the whole globe. So we're going to start by picking one of these tiles. Let's choose this one. And these data are provided via OpenDAP. So OpenDAP provides a way of allowing you to stream data over the internet without you having to download it to your own computer first. So what you can do is take this data URL, and you can copy that into your script and use it in the same way that you might use some absolute file path to some file on your computer. We can see from the access form as well that the data have four variables. We have the latitude, longitude, and Z, which is the altitude. And we have this CRS variable that tells us about the geographic coordinate system. So let's take this data URL now and copy this into Python. If you do go ahead and use these data in your own work, please make sure that you cite them properly. You can see the citation listed here on the landing page. So let's start by importing a module. Let's import xarray as xr. Make sure you install that if you haven't got it installed already. We can provide our data URL. So I'm going to copy that in here. And then to load those data, it's as easy as ds equals xr.open datasets and our URL. And then if we want to preview those data, we can just do print ds, and let's run that. After a few seconds, you'll see the data printed in the terminal. We have two coordinate variables, the latitude and longitude, our CRS variable, and the relief data here, Z. We also have some global attributes that describe the dataset as a whole. Ideally, I would like to see this be a bit more extensive than this, but I have a whole video on how to write netcdf files properly, so if you're interested in that, go and watch that. Let's restore the panel, and we can get rid of this print now. If we want to plot those data, we can import a different library. As import matplotlib.pyplot as plt. And if we go down below here, we want to plot our variable z, so we can do that. DSZ in square brackets dot plot, and underneath that plt dot show. And if we run that now, we can see that the data have been plotted here. Nice and easy with just 6 lines of code. This did, however, take quite a long time to run, So what we could do first to speed up the process is to resample the data by selecting every 10th point in both latitude and longitude, at least while we're developing our code. And after that, I'll show you how to make this plot much nicer too. So I'm going to close down this preview here and we'll return to our code. So let's resample our data. I'm going to resample the data using a factor of 10, meaning that I want to select every 10th point of latitude and longitude. So that should be just 1% of the points afterwards. I'm then going to create a new X-ray object called ds resampled. And I'm going to do that by using our original object, ds, and using isel, which is selecting based on the indices of the data. And let's create a new line here to make this more readable. And we're going to select based on latitude. And we do this using a slice. As we can see from the description here, this allows us to select based on some start and stop index and the step that we want to select. Well, in this case, I don't want to specify the start or stop, so I'm going to use none. But I do want to specify the step, and that's going to be my sampling factor, which is 10. I've put a comma here, and we're going to do the same for longitude. So I can just copy this line and do exactly the same thing. And then instead of plotting this object ds, I want to plot ds resampled. And let's try and run that again. And if you're coding along, you should have noticed that should be a lot quicker now. So now let's try and improve this plot. Perhaps the first thing that we want to do is add a map projection to the data. So I'm going to close this again here. So to plot the data on some defined map projection, we need to use a new library that's called Cartopy. So import cartopy.crs as ccrs. And we can go and look at which projections there are available. So I'll put a link to this page in the description. This is just a list of different projections that are available through Cartopy. There's plate carré, and it tells you some arguments that are recommended. And if you scroll down, there's a number of different projections you can choose from. So let's say I want to use Mercator. We've imported this cartopy.crs as ccrs, which means we should be able to just write ccrs.mercator and any of these arguments that we might want to add. So let's show you that in the code. We can make some space here, and I'm going to reduce the size of my terminal a little bit as well. And let's say projection equals ccrs.mercator. We don't want to use X-Array's inbuilt plotting functionality anymore. We want to use the full functionality of matplotlib and Cartopy. And that means we need to initialize the figure and the axes first. So let's go figure ax equals plot.subplots. And I'm going to do subplot kw equals, and then a dictionary, projection, and the value is projection, which we've defined here. And we can define some size for our figure as well if we like. Let's do fig size equals, and in a tuple, so that's round brackets, 6 by 8. And then I'm going to remove this, but I'm going to write the relief data to a variable called relief. And we also need a transform. So let's do transform equals ccrs dot plate carré and round brackets. So why do you need a transform? Well, a transform is basically the coordinate system in which the data is provided. And so if the data are provided in regular lon lat coordinates, we use plate carré. So now if we want to plot these relief data, what we can do is go im equals relief.plot. we need to define the axis we want to plot it on, which is x, as we defined up here. And we need to specify the transform as well, which is equal to transform. So let's have a look at that now. And here we can see a plot of the data. But what we have lost is the longitude and latitude information. And that's because we need to add some grid lines. So let's go and do that. I'll create some space here, and we're going to scroll down a little bit. So let's add the grid lines as an object GL. And that's equal to ax, our axis object, dot grid lines. I'm going to open some brackets. And we need to specify a number of different arguments here. We're going to specify a projection, so CRS equals transform. We're going to say the width of the grid lines, line width, equals 0.5. Feel free to adjust that as you like. I want them to be grey. We can define the transparency with alpha equals 0.7. Maybe the line style. And if we want a dashed line, we do this. By default, I think they're solid lines, which is like this. And I want some labels as well. So draw labels. Oops. Labels equals true. And here you can see we've added some basic grid lines. The next thing I'd like to change is the color palette that we're using. So we're going to use a different library. If I go back to my code, and this library that we're going to use is called cmocean. And this specializes in providing different color maps that can be used for oceanography. So I've put a link down to this page down in the description. And there's a number of different color palettes that you can choose from. The one that I'm going to use today is this Topo color palette. So let's go and do that. I'm going to define this here with the other variables. cmap equals cmocean dot cm for color map dot topo. And then here, where we have this relief plot, I'm going to add a new argument. cmap equals cmap. And let's try and run that. Okay, this is starting to look quite nice. The next thing I'm going to show you how to add is some contours. So to do that, we're going to need to use a different library. We're going to need to use NumPy as NP. And we're going to use this to create an array of different values for our contours. So let's go down here, and let's say we want our contour interval to be every 500 meters, for example. And let's say we want these contours to begin at vmin equals minus 4,000, and we want them to end at vmax equals 4,000. Then we need to create an array that extends from minus 4,000 to 4,000 with intervals of 500. So we can do contour levels equals np for numpy dot our range. We specify vmin, vmax, and also contour interval. Now, the peculiar thing about this is because there will actually be a contour on 4,000, because 4,000 is some value within this array, the highest value in this array will actually be 3,500, not 4,000. So we're going to get around that by, instead of specifying vmin and vmax, we're going to specify vmin and vmax plus contour interval. This is just one of the quirks of how this function works. You can see this on the description. If you hover over the function, the values are generated within the half-open interval, 0 to stop. In other words, the interval including start, but excluding stop. So anyway, we've created this array. Now we want to plot our contours. So we can go a little bit lower down now, and we'll plot the contours before the grid lines. So relief dot plot dot contour, and then there's again a number of arguments that we need to give here. So levels, and this is the contour levels array that we've just created up here. We have ax equals ax, transform equals transform. We can define the colors for these contours. So colors equals black. And let's define a line width as well, maybe 0.5. So I'm going to save that and run it again. And there we go. I guess the elephant in the room is now that the color bar is a little bit too large and is also overlying our grid line labels. So let's try and adjust that. What we actually have to do here is disable where the default color plot is being plotted and create our own manually. So let's do that. So to disable the color bar, firstly, we can go to where this relief has been plotted, and we have this argument, add color bar, which by default is true, but we can set this to false. Then I'm going to scroll down to the bottom and add the color bar. So first we need to create an axis for this color bar. So cbar ax is equal to fig.add axes, and then in round brackets. And we need to define the outline of this axis. So this is going to be a list in square brackets within here. And we define the left, bottom, width, and height. So I have some values that I've tested before. We're going to go with 0.87, 0.25. So that's left and bottom. The width, we're going to use 0.03, and the height, 0.5. I'm also going to scroll up here and I'm going to remove this manual figure size that I added earlier. You can, of course, add that again if you want and tweak the color bar to how it fits. Then we're going to do cbar equals fig.colorbar. And we want the color bar to be for our im object that we created up here, the relief plot. And the c-ax, which is a color bar axis, is going to be this cbar ax that we've just defined. The final thing is then to add a label to this color bar. So cbar dot set label. We're going to call this relief in meters, and we're going to use font size equals 12. So let's have a look at this. We might need to tweak these numbers if it doesn't look right. And there we are. I can just extend this preview panel. We should then be able to see my label. I did notice down in the terminal that the line width has not been acknowledged in the contours. Good job if you spotted that earlier. That was just a typo. It just needs to be line widths, plural, instead of the singular. So we'll run that again. And there we go. Those contours are a bit less bold now. So now, what if we don't want to plot the whole tile, but we just want to zoom in and plot a small region, like up here, for example? Well, we can do that. If we return to the code here, where we resample the data, we can remove this code and the sampling vector. And this time what we're going to do is ds.cell instead of isel that we used before, because this time we're selecting based on the actual latitude and longitude as opposed to the indices. And we're selecting based on the latitude. And again, we're going to use a slice. And the values I'm going to use this time is 26 and 30. And for the longitude, another slice between 51 and 58. Now, if I save that and run it again, it should be as simple as that. And after some time, there we have it. And we might need to increase the size of this plot. And then the color bar is not overlaying our axis. What I'm going to show you how to create now is this 3D plot of the data. It's interactive, so you can zoom in, you can rotate the plot round, You can place your cursor wherever you like and you can read off the bathymetry from that point. The data that I'm showing you here is from the Strait of Gibraltar. So we're going to take data from a slightly different tile to what we've been using before. I've chosen this region just because the relief around here is quite cool, both above and below sea level. So let's close this now and we're going to create a completely new script. So this time there's only 3 libraries that we're going to use. We're going to import numpy as np. We're going to import xarray as xr to load in our data from netcdf. And we're going to import plotly dot graph underscore objects as geo graph objects. And this is going to help us create this interactive plot. So the tile that I'm going to use this time is north 45, west 15. Let's go to the opened app data access form and we can take this data URL. So again, we can do URL equals this data access URL. Let's load in the data again. So ds equals xr.open dataset and our URL. Let's create a subset of this. So ds sub equals ds.cell. And this is nothing new so far, but we're going to use a slightly different range this time, of course. So lat equals slice, and the region I'm going to select is 34 to 38. And lon equals slice -7 to -3. Just bear in mind that at 15 arc seconds resolution, this is still quite a lot of data points. So it's going to take quite a long time to work with this, and if you need to subset the data further first, whilst you're testing, please go and do that. I have the magic of editing, so you're not going to have to wait around while I run the script each time. I just want to take a look at the data again, so we're going to do print ds sub, and we'll have a look at those data. So let's enlarge the terminal. And what I want to point out here is that latitude and longitude, these are the coordinate variables, have only a single dimension, latitude or longitude, which means that these are just one-dimensional arrays. Whereas z, our relief, is a 2-dimensional array with both latitude and longitude as the dimensions. Now, in order to plot the data with plotly, we also need our latitude and longitude to be 2-dimensional arrays of data. So let's go and make those grids. The first thing we're going to do is just load in the data into variables that are easier for us to work with. So let's go lat equals ds sub, and the name of our variable is lat, and dot values to just extract the values. This will then be a 1-dimensional numpy array. We could do the same for lon, so equals ds sub and lon dot values. And z, we can also do the same, so equals ds sub z dot values. But remember, this is a 2D array, whereas this is a 1D array, as is this. So we're going to use NumPy now to create these 2D arrays of latitude and longitude. So I'm going to do lon 2D, lat 2D is equal to np dot mesh grid, and in the same order that we've written here, we do lon lat. And let's just print this so you can see what's happening. So print lon 2D, and we can see here in the terminal we have this 2-dimensional array, where for longitude every line is exactly the same. So now let's try and create a basic plot. I can remove this print. I'm going to scroll down a little bit to give us some more space. And let's do fig for figure equals go dot figure. Go is the name we've given to this library up here. Let's open some brackets. And as the description below says, the first thing we need to give is the data. And this itself is going to be equal in square brackets to a go.surface. Remember that capital on the S. So now I'm going to create a new line. What we're going to do is create the surface, which is going to be plotted on our figure. We need to give it a few different arguments. So we can go x equals ln 2D, y equals lat 2D, and z equals z. And to present that, we need to do fig.show. So we're going to try and run that and see how it looks. And after a small wait, a new tab should have opened up in your browser, and you should see something like this. Already this is quite useful. It's interactive. We can rotate round. We can have a look at what the elevation is at different locations, but it perhaps doesn't look as nice as we would like it to. You might have found it a little bit laggy when you were trying to interact with the plot, so instead of writing out this preview, we can instead write the data to an HTML file, and then we can open this and interact with this how we want. So to do this, I'm going to comment out this fig.show temporarily, and we're going to do fig.write.html. And then we've just got to put in the file path to where we want to write the data. So if I can do something like interactive 3D relief plot.html. And if I run that, and after a while we can see that this HTML file has been created here. So I'm going to go and open that in my browser. And here it is again, but this time I can interact with it a little bit more quickly. So now let's go and improve on this plot. So the first thing that we're going to do is create some custom color scale. So I can do this here, custom color scale, and this is equal to some list. And within this, we need to include pairs of values and colors, where the values range from 0 to 1. So in its simplest form, you could do something like 0.0, and the color I could choose could be navy, and I could choose for 1 some color, maybe saddle brown. And the color scale would transition between navy and saddle brown between 0 and 1. Now our relief is not between 0 and 1, but still when we apply this here, we can do color scale equals custom color scale that we've just created, and that range will extend over the range of Z values. Now I don't want just a color scale that transitions between two different colors. What I really want is to be able to see a sharp transition at 0 meters at sea level. So what we're first going to do is compute what our minimum and maximum values of Z actually are within this region. So we can do Zmin, Zmax is equal to Z.min, Z.max. And what we now need to do is work out exactly where on this scale between 0 and 1 our sea level actually is, where Z equals 0. So we can do that by doing sea level is equal to 0, which is sea level, minus Zmin, and we're going to divide that by this Zmax minus Zmin. So what have we done here? We've worked out how deep the water is, and we've normalized that value by the elevation range of the data to work out what fraction of the total range the sea level is above the maximum depth. We'll be able to see whether that's correct on our plot if you didn't follow the maths there. And now we're going to input some values, sea level, deep sky blue, and then we're going to assign another value, again at sea level, and we're going to assign a different color, light green. So what we've done here is assign two different colors at the same point along our color scale to say that we want a sharp transition in the colors here. So between our minimum value of Z and sea level, the colour will transition between navy and deep sky blue. And above the sea level, the colour will transition between light green and this saddle brown. So let's try and plot that. So here's our new plot with the new colour scale. And if we move our cursor to close to where this blue changes to green, we should see that this occurs at exactly Z equals 0, or as near as you can get your cursor to that. We're going to do some more edits now to just improve the visual appeal of this. First thing we can add is a colour bar, and that's equal to a dictionary value with title equals, let's say, relief in meters. We can assign some lighting. This is again going to be a dictionary. And there's some different arguments we can add here. I'm going to add ambient equals 0.8, diffuse equals 0.5, specular equals 0.2, and roughness equals 0.9. I see my typo here. There's a nice explanation about lighting on the Matplotlib webpage and explains what the different lightings are, and has some different examples of what the different lightings look like. What we're also going to include is some contours, and this is again going to be a dictionary. And we need to define that we want our contours to be applied to Z, this up here. So then we have a nested dictionary. So then we can add some attributes, so show, and this is going to be true. We can add use color map and make this also equal to true. We can add a highlight color. This is going to be the color that the contours are highlighted at when you make contact with them. Let's make this lime green. We can also project them to the axis below using project. We want to project them below the surface, so we can do Z true. So let's have a look at that now. That's quite a lot of changes. So here we can see the contours now have been plotted on here. The contours are the same color as the color map. And if we hover our cursor over the plot, we can see below the plot we have this lime green contour, which is the contour at the elevation of the point that your cursor is selecting. And they're projected in the Z direction below here. So I hope that helps you understand what the different contour arguments mean. What I'd like to do now is just add some annotations to this plot. And I'd also like to adjust the aspect ratio so it's a bit less exaggerated in the Z direction. So let's close this one more time. And below this now, in a new function, we can do fig.update layout. We can open the brackets. Let's add a title. This is equal to a dictionary with different parameters again. So the text that we want to add as the title, let's make this equal to 3D relief plot Straits of Gibraltar. I want to specify that I want this title to be in the center horizontally, so x equals 0.5. And x anchor, specify that I want the center of this text to be at 0.5, halfway along. And we can specify a font size as well. Font is then another nested dictionary. Dict size equals, let's go for 24. We can also adjust the axis, which is called a scene in this case. This is again a dictionary. You see how things are now with Plotly. Let's add some axis titles. So x-axis title. I'm going to make this longitude. y-axis, title, latitude, z-axis, title, relief, and the aspect ratio, this is going to be, again, a dictionary, and we're going to say x equals 1, y equals 1. We're going to adjust the z scaling, so z equals 0.2. So this should reduce the vertical exaggeration by a factor of 5. And now let's have a look at that. And I can see that I've made a typo here, aspect ratio. It didn't like this. This should be, I believe, without the underscore. Let's try this again. And there we have it. The camera is quite high up in the sky now. We can adjust this if we like, of course. We can go and zoom in. And this to me looks a lot nicer than it did before. We can adjust where the camera is by default when the plot is first configured. To do that, we need to add a new argument into this dictionary here for the scene. It's going to be camera equals dict, and it's going to be the eye of the camera, so where we want the eye to be, equals dict. And I've played around with these numbers before, so I know what to input here. So x equals 1.5, y equals 1.5, and z equals 0.7. If you're looking at a different region, I'm sure it will take a little bit of time to find something that works for you. And let's have a look at that one more time. And there we go. I think that looks okay. If you found that interesting and or useful, please like and subscribe. There's going to be lots of different videos in the future where I'll show you how to work with different interesting datasets. Thanks very much for watching. I'll see you next time.